start the third round of the debate. Okay, the opponent please propose one problem.
We would like to challenge existential line, which is problem 8.
Number 8. Yes. Okay, this is problem number 8, equipotential line.
I'm the reporter of problem number 8, equipotential line. This is the flowchart of my today's presentation. First, I'm going to talk about the problem statement. Next, I'm going to present the phenomenon that is being stated in the problem statement. Third, we are going to present our theory about why exactly this phenomenon takes place. And fourth, we're going to conduct some relevant experiments to prove our theory and discuss some other parameters. And then last, I'll do a summary and conclusion. The problem statement is that when we place 2 electrodes in the container of water and apply a safe voltage to them, using a multimeter, determine the electric potential at various points of the liquid, explore how the found equipotential surfaces correspond to possible assumptions for different experimental conditions and for different liquids. And our focus is that, first, before even conducting the experiment, we should first predict the shape of the equipotential lines. Second, we should observe the equipotential lines under different parameters, such as different electric potential differences and different solutes in the solution. And last, we're going to explain the difference between the real condition and the theoretical condition. And our theory is that the fundamental assumption is that when the circuit is triggered, the transfer of the electrons will create electric fields. The charged particles of the external electric field are subjected to the force exerted by electric field, and the potential is the electric energy possessed by a unit charge. And here we're going to first make an assumption that we imagine the electrodes as long conducting wires that is directly perpendicular to the water surface, so that we can use the following formula for the electric field. And the experimental data that I'm going to show later supports this assumption. So I'm going to talk about how we arrive at this conclusion. First, by assuming the electrodes as long-conducting wires, we can get this formula. And since we know electric potential is the integration of electric field, we integrate this and we get this. And then since we have 2 electrodes, one at the left and at the right, and so we add them together and we arrive at this conclusion. Basically just adding these 2 together. And this is also before we conduct our experiment, we plot the we plot this into a 3D space, and then the XY coordinates here are the surface of the water that we're going to experiment, and the Z coordinates is electric potential. And from this, we can first determine the equipotential lines that we're expected to see after we conduct the experiment. And a few predictions that we can make using the mathematical formula is that since x squared and y squared terms exist in our formula, we can assume the shape of the equipotential lines being logarithmic, as in the natural log function exists in the formula, and that the x-axis and y-axis should both be the axis of symmetry, meaning that along this line and this line, the image should be symmetric, and this assumption is also verified in the following experiment. And here are our experimental equipment. First, we use a digital multimeter as the voltmeter stated in the problem statement, and we use this to probe various points inside the shallow dish of the solution. Second, we use a couple of weights, and then we use them as electrodes. Third, we use the shallow dish, which has a little compartment for the graphing paper we show here, so we slide it under it, and we use the graph paper to introduce the coordinate system in our experiment. And here are a few ingredients that we use. First is water as the reference, and then we use the saturated potassium chloride solution and saturated sodium chloride solution. And last, we use a lab power supply to apply the safe voltage mentioned in the problem statement. And this is our experiment setup. It's very easy to understand. First, we place the graph paper under the shallow dish. Before that, we mark out several dots on the lattice grid, on the lattice points on the graph paper, and then by applying a voltage using the lab power supply over it, and we place the 2 electrodes in their respective places, and then last we fill the dish with a really shallow layer of the solution that we're going to test. And why we are using, we want it to be as shallow as possible, we discuss later. And then last, we use the multimeter to probe each of the points shown here, and then get our equipotential line. Next. Okay, so first, this is our experiment data. The way that we get these lines is that because we measure the points on the lattice grid, and then we get like a array of data, and then we put this array of data into a MATLAB function that is used to plot contour lines in geometry. Because equipotential lines and contour lines, which is the lines that have the same type as used to describe a landscape, is practically the same. So we just like modified that function, and then we used it to plot this. So this is actually an estimated line. But these lines are really close to what is actually the real lines, because the change in electric field is smooth, so there will be no intersections like the ones that will probably happen in geometry. And this is really close to the real situation in the liquid. So other than some slight deviations, using pure water at different electric potentials, which is 3 volts, 6 volts, and 10 volts, the shape of the equipotential lines are really similar. The reason why the lines are looser at the 3 volt side and then denser at the 10 volt side is that the electric potential difference between each line shown here are all 0.2 volts. So they will have 15 lines here, and then they will have 50 lines here. The analysis of the previous 3 images shown is that according to the formula in our theory, since the same kind of solution will have the same boundary condition, the boundary condition being the coefficient at the front of our formula, therefore the results will look really similar. However, since the initial voltage is different, the phi value will be different. And if the phi value, if everyone forgot what phi value is, I have shown it on the right. It is the initial electric potential difference that we apply, like 3 volts, 6 volts, and 10 volts. The second experiment that we conducted are using different types of electrolytes. The first is water, and the second is saturated potassium chloride, and the last is saturated sodium chloride. And when the solution is different, the shape of the equipotential lines also look very different. We will discuss about these deviations later. Different solutions have different boundary conditions because they have a different absolute value. Thus, the distribution of electric potential will be different, which leads to the different density of the equipotential lines. Next one. Now, I'm going to talk about the difference between the real condition and the theoretical condition. There are 3 main deviations that we have observed. First, the equipotential lines around the electrodes observed from the experiment are diamond-shaped instead of the round shape that we predicted. Second, the equipotential line curved towards the electrode at certain regions we believe that it's because of the disassociated anions and cations flowing toward the opposite electrodes forming the electric field lines. And allow me to explain this clearer. Because as we're conducting the experiment, we are in reality conducting an electrolysis in the background, because we have a solution of soluble salt, which is the electrolyte, and we are applying voltage to it, so it's electrolysis. And when electrolysis happens, ions disassociate, and then they move towards the respective, the electrode with the opposite charge of themselves. So, and I'll discuss about more of this later. And the third, the equipotential lines are denser around the negative electrode and looser around the positive electrode, which I'll also discuss. The reason why we believe the equipotential lines that we draw to our experiment data are diamond-shaped is because of how the lines are being plotted. So, as you may recall, I've mentioned that we plot these lines on the lattice grid. So, for the round electrode, we actually have 5 points, that is, like on the coordinate plane that is being covered. So, when the function tries to simulate what the equipotential line may look like, it tends to wrap around these points. So you have a cross, and then it wraps around this cross, so making a diamond shape. So this is not an experimental error, but rather a plotting issue. Next. Why do the equipotential line curve towards the electrodes circled out? The phenomenon I'm talking about here is that, now I use the blackboard. Sure. So this is the electrode with the lower electric potential and higher one. Let's assume it's 5 volts. So let's assume that potassium cations and sodium anions are present in the solution. So as when the voltage is being applied, the anion will flow towards the positive electrode, and the cation will flow toward the negative electrode. But as they have the same, they will follow the electric field lines as they flow to the electrodes. However, since they all have the same charge, they will repel each other. So we hypothesize that they will not, they actually move like this towards the electrode. However, the density of them will be slightly lower here and more here. So you can view them as traveling in this direction. So after seeing the line there, we can deduce that, well, in theory, it should look like this, because there are negative ions or anions traveling to the electrode. Along this path, the electric potential will be lower than what we expect. So the equal potential lines will have to curve toward the electrode. So this is the phenomenon that we observe. Next one. And while the equal potential lines denser around the negative electrode, this is a very interesting question, and we believe that this is because when we perform electrolysis on potassium chloride, for example, we're actually electrolyzing water because of the reduction potential and oxidizing potential differences. However, because the weight is metal, the negative electrodes will have hydroxides precipitating out, whereas the other side won't. So the conductivity here will be better, and this side will be worse. So the electric field lines the equal potential lines will come this way. And these are our conclusion and summaries. First, the ideal potential line is related to the natural logarithmic function. Second, the same liquid have similar equal potential lines, but the initial voltage will affect the density of the lines. And last, the value of epsilon, which is associated with the solution type, will be different. Therefore, the equal potential lines will vary between different solutions. This is our reference, and this is the end of my talk. Thank you.
Okay, so hello everyone, I'm the opponent for MD Ming Dao Mei M. And so I'd like to make some clarifications first. So first of all, how did you conduct your experiment? Did you change the waters throughout the experiment?
No, we did not.
Oh, so you did not change the change the liquid throughout the experiment.
Yes.
Okay. And how long does your experiment usually take?
About 2 minutes.
About 2 minutes.
Yes.
Okay. How did you record the data? So I saw you recording the data from a coordinated plot.
Yes. We have 2 papers. That is, one is under the. So we just transcribe the data on.
Okay. Then have you ever considered the error of refraction probability?
Refraction?
I mean, for example, for a straw, and when you look at through the liquid, maybe it might differ a little bit.
That is possible. So as we conduct the experiment, we meticulously look at directly above it, so as to minimize the refraction.
Have you taken into account the occurrence of electrolysis, like you just mentioned? I believe you do so, right?
Yes. So.
Okay. So what do you believe are the products that will be generated after electrolysis of NaCl?
After NaCl has been electrolyzed, on the negative side, no potassium metal will come out. So at that side, only hydrogen will come out.
I mean NaCl not.
Sorry. Sodium will not come out because of the reduction potential.
Oh, sodium will not come out.
Yeah, it will not come out. So only hydrogen will come out.
Okay.
And
hydrogen?
Yes, hydrogen. Because hydrogen has a positive charge, and so has sodium. So
not Cl?
No, because Cl is on the other side.
And then what about K plus KCl? What are the products of those?
Some of the potassium ions that come to the electrode will react with the electrode itself, forming some. Because the electrode is made of iron, and we all know that.
Okay, well, I'll ask you later. Thank you. honorable judges and fellow competitors. I'm the opponent from Lingdao Mei M, and today I'll be opposing problem 8, equipotential line. So the key points for me to this problem statement is the expectation. So we have to consider how our expectations deviate from different conditions in liquid. So conditions and also the expectations are what I think are the most important things. So some summary of the reporter. First of all, the theory. So they use electric field equation and also electric potential equation. For experiment setup, they use paper with coordinates and multimeter, dish, electrode, water, KCl, and NaCl as their main liquids. Second, parameters. They change different potential difference and different solutions as well. For data, they didn't really provide their theoretical data, and equipotential line is only assumed. Some advantage for the reporter are that, firstly, the overall structure of the presentation is well thought out, clear understanding of the experiment clearly, well demonstration figure, and clear derivation of the theory. Some suggestions would be that some essential parameters are not considered, and they didn't really take into consideration of the products of these electrolysis process, which could affect the electric potential throughout the entire basin. Then thirdly, they should not use the assumption experiment theoretical value. Setup, one advantage to that was they have great and clear photo. So some suggestions would be that they could have more systematic error with hand-drawn coordinates. They could consider more solution that is being used since the product of the electrolysis can differ between different solutions. Then they didn't explain why they chose to use DC power supply and the possibility of using AC, as the problem statement asks to consider different conditions, but they didn't seem to consider too many conditions regarding AC and DC. Lastly, some of the parameters are not kept. Hey, some of the parameters are not. So for theory, one advantage is that he has clear explanation behind the phenomenon. Suggestions would be that he could probably calculate for the actual difference between the theoretical data rather than the experimental data. So for experimental data, advantages, clear data, suggestion, they could provide theoretical data for better trend, and they could specify the use of DC and AC power supply. And unit is missing from some of the charts. And they also need to consider more parameters to show other trends and to answer the problem statement. So this is going to be my discussion structure. I'll still make some clarifications as some clarification points were not made sufficiently. And then I'll move on to the setup and experiment. And then finally, some additional parameters that they might need to consider further on. So I'd like to start the discussion right now. Okay, so first, I'd like to clarify some points furthermore. So first is, can we please go to page 5? So is the x is the z axis positive and negative?
Yes.
Okay. And how would you describe the curves from this? Would you describe it as hyperbola or parabola or?
Well, it is neither parabola or hyperbola. When we place the two electrodes very far apart, the lines in the middle will be very close to hyperbola, because that's how hyperbolas are being defined. Because hyperbolas are defined by the points that have the same difference from the two focal points. So this is an electric potential difference problem, and so when.
So you're saying that this is not a hyperbola? Or?
It is not, but when we place the two electrodes very far away, it will be very similar, like it will degrade into a hyperbola. In reality, it's more complicated.
Okay.
Because the reason why it's not hyperbola is, you see, there are circles here. It's not hyperbola.
Okay. And so I'd like to start off my question from the problem statement. So as I just mentioned, one of the most important factors in the problem statement is probably the deviation between your expectations and the results. So I'm wondering if you've shown your expectations or your hypothesis regarding the results.
Yes, we do.
Okay, can you please show me?
This is the.
Oh, so you're using the theoretical value as your expectations. Okay.
Yeah.
I like to ask, have you considered different conditions, like other than liquid and voltage?
No, we have not.
Okay, so basically you only consider liquid and voltage. So now I'd like to probably suggest you to probably come up with some other parameters. So I'll go first. I think changing AC from DC will also affect the result. I'm wondering whether you use DC or
yes,
AC.
We use direct current.
Oh, so you use direct current. How would you think if you change it to alternating currents?
By changing to alternating currents, I think the lines will not really change. Although the meaning of these lines will change as the electric potential switches. Because the ones that means 1 volt here may mean 4 volts in the next shift as the alternating current shifts.
Okay, so this is what I think if you change to alternating current. Because alternating current basically have current that are alternating pretty much. So I believe what the graph will look like is both sides will be pretty much symmetrical.
Yeah.
Okay. I think other than symmetrical, I think it will actually be more accurate than using DC because when the currents are alternating, the products generated through electrolysis might be more distributed, evenly distributed throughout the basin. Do you agree?
Yeah.
Okay, thank you. So that might be something that you can try to verify next time.
Yes.
Okay. We'd also like to ask, so for time, you said that you measured all the dots under 2 minutes.
Yes.
So can you please go up to the coordinate plane that you showed? So you dotted all the dots under 2 minutes?
Yeah, roughly 2 to 3 minutes.
Okay. So here's my concern with time. Because we all know that as time increases, through electrolysis, more products will be made. And those products are acting like resistance. So which means that the accuracy will definitely decrease as if there are more resistance, the data will definitely deviate more. So if you're doing this experiment under such long time span, I'm wondering whether the data you collected at first will differ from the data you collected at the end.
The way that we deal with this problem is not perfect. What I'm going to tell you is that because the way we do it is from one side to the other side. So in order to average out the problem that you just stated, because we use DC not AC, we first probe it from the left to the right, and then we probe it from the right to the left, and we average out the results. But this is still not the perfect way to resolve this issue. So can you please give me some suggestions on how to improve this fact? Other than alternating currents.
Because we all know that after a certain period of time, and that is probably like a very short time, was probably within 1 minute. So I think my suggestion, I'm not sure whether this will work or not, I'm just suggesting, is that maybe you can divide your experiment into different times. So you basically probably conduct the points around this point, and then you change the liquid afterward. So basically conduct this experiment under different time zones by dividing this plant into several sections. So that's just my suggestion. I don't know if
sounds very plausible.
Yeah. So because that definitely definitely decrease the possible deviations generated through time. Yes. So that's something you can also consider as well. How many points did you plot on this graph?
19 points here, 11 points here, so it's 209 points.
But you did minus these 4 points and this one as well.
Oh yeah, so it's 199. So we assume all these as 0 volts if we use 0 volts, and all these here are 5 volts if we use 5 volts. Negative here, positive here.
So the equation that you use are for point electrode.
Oh no, for a long conducting wire.
Oh, for a long conducting wire. Then if your electrode is a long conducting wire, then because in your experiment you're using basically a cylinder as your electrode, right?
Yes, correct.
Then how does a cylinder compare to a long conducting wire? Are they the same?
In this case, we believe that they are the same because the cylinder is perpendicular in the water. Just like, because the electric field around the long conducting wire will be circles.
Yes.
So in this case, we assume that, and then in our experiment, it's very close to our theory. So it further implies that our assumption here is correct and is valid.
Okay, then I'd like to clarify something. Then do you think the width of the electrodes will affect, the radius of the electrode will affect?
Yes.
Oh, so you do think so. So maybe that's something that you can add to your experiment further on.
Yes.
Okay. Then. Okay. So can we please go to page 15? So could you explain why there's a difference between an A and CL? Is this the problem with the products that they create?
Oh yes. I haven't explained it clearly. Sorry. Because I believe that when electrolyzing sodium chloride, it's basically electrolyzing water.
Okay.
No, of course with some chlorine appearing here. So well, here we will have sodium. Sodium cations here. So we'll have, because one side will perform some chlorine ions, well, chlorine gas, the other side will not. The ion density here and here will be different. And ion density can influence the resistivity, and since the electric potential difference between these 2 points will not change, so the electric equipotential lines will shift. It's just like the potentiometer in electric circuits.
Okay, I understand. So for water, it seems like it is pretty symmetrical, right?
Yes, correct.
But I'm wondering, because we all know that through electrolysis, that's the per unit time. So it can be predicted that with one atom of oxygen being created, there should probably be 2 hydrogens. So meaning that the overall product generated through electrolysis on this side, which is the negative side, might be a little bit more. And since hydrogen atoms are actually larger in radius and also volume than water and than oxygen atoms, so do you think so? Do you still believe that they will be symmetrical? Because to me, since the amount of atoms being created
there
are
are
different.
2 points that I would like to clarify. First, hydrogen atoms are not bigger than oxygen atoms.
Oh,
yeah. And second, because the hydrogen atoms, and you know that the water dissociation constant is 10 to negative around 14. So in this case, the resistivity of water, pure water, is very, very high, and the effect of ions are not that pronounced.
Okay.
So, of course, in order for electric current to flow, there are ions, but the hydrogen and oxygen ions that is dissociating in the water is very slight, and it is absolutely not pronounced. So it pretty much looks like the theory.
So you still believe that they will be symmetrical?
Yes, symmetrical.
Okay. So for me, I personally still believe that due to the amount difference, that the data right here will deviate a little bit even more from the positive side. So that's my own opinion. So that's open to discussion.
Debate? Yeah.
Yeah.
Oh, yeah.
So did you consider the probability that some products will not escape other dissolve or other dissolve?
They will dissolve, like for example, sodium and potassium will not appear in the water because they react with water immediately. So unlike chlorine gas, which will escape and poison us, this side will not have metals coming out, and instead the ions here will just accumulate.
Oh, so they will just accumulate. Okay.
Yeah.
So if they accumulate, then why are this data still so accurate?
We'll answer.
Oh, okay. So overall, from our last discussion, I basically suggested them to follow the problem statement, and the problem statement asked them to first provide their own expectations and then also provide other conditions. So that is what I suggested them to do by giving them some relative parameters that they should also consider. And also, time is another thing that they should also consider. As throughout time, more products will be created, and that will be inaccurate. So during this discussion, we mentioned the importance of the correction to the theory equation they have provided, and we have clarified some confusions about the graphs and the theory as well. And they really did a good job on explaining their reasoning behind their decision. they told us that they did not consider other conditions under other rather than H2O and these three, so which I believe they can do a lot more, and they believe that the suggestions given to them were really plausible. So that's a good thing that was mentioned from our discussion. Thank you.
Okay, thank you. Please come over here.
Right.
I have a couple of quick yes and no questions that I'll ask both of you. So first, Mr. Reporter, did you consider the Gui-Chapman model or the Boltzmann-Poisson equation that was already existent?
No.
You did not. Do you think, Mr. Opponent, that the boundary conditions, like metallic boundary conditions, Dirichlet boundary conditions, will affect the shape of the equipotential lines?
Can you please define the second term you used
Okay,
for
sorry.
boundary?
So metallic and non-metallic boundary conditions.
So I personally believe that it will affect.
Yes. Okay. So you mentioned that you measured the entire experiment in the first 2 minutes.
Yes.
So I also noticed that you have 200 points to measure. So do you measure like 50 points a second or something?
No, we have multiple people.
Okay, that's great. Did you consider the fact that there are stable regions as the ions move across concentration? So the most stable time period for measurement is actually between 5 to 10 minutes.
No, we do not.
Okay. Do you think that it would be better to measure something when it is more stable or when there are confounding variables present?
I think this is very contradicting because we all know that as the time increases through electrolysis, more products will be, more resistance will be made. But you still have to measure it with, after 5 minutes. So I think that's something that they should also do an experiment on separate lab and then compare the results.
Okay, yes, I agree. Mr. Reporter, the opponent mentioned earlier that there were more hydrogens than oxygens, so they would skew the symmetry. But I think that hydrogen is plus and oxygen is 2 minus. So I think 2 hydrogens, that's 2 times 1, that's 2, that's equal to 2 minus, and they cancel out. Therefore, they would produce symmetric results. Do you agree with this?
No, because while the results are symmetric, the results, I do not agree with your results. Because unlike the case with sodium and chlorine, hydrogen and oxygen, the concentration of hydrogen ions and hydroxy ions in the water is very low. So I would just completely neglect that in this case.
Do you consider the neglection of the z direction equipotential lines?
I think that should be considered.
Yeah, I also think that should be considered too.
Wait, can I actually answer to that question? That is the exact
Sorry,
reason.
you cannot.
Oh.
Did you consider an electric double layer effect?
What? No.
Do you think an electric double layer effect will be important? An electric double layer effect occurs in the Stern layer, whereas
So
the
I don't really know that term because that
okay, we have
something
plenty of
that we
time.
discussed.
Excuse me.
Okay.
So as this is the cathode, and as the negative ions move over here, they're going to create their own electric field, which is going to skew the distribution of the electric fields. But the report did not mention that. Do you think the electric field that's produced by the adherence of anions will have any effect?
Yeah, I think that will definitely have some effect.
Okay, thank you. That summarizes my questions. I was trying to call the reporter and he said, don't school. Okay, I'll be reviewing number 8, equipotential lines. So here's a problem statement, you can read it yourself. The main focus is on what are the relevant parameters, to what extent do various experimental conditions affect the overall formation, how do redox reactions contribute to the double layer effects. So here's the reporter's performance. He has an explanation for why the phenomenon occurs. The theory did not use nor apply an already existing model, which I think I'll talk about that later. An experiment, there was no clear comparison from theory to experimental data, and he lacked data overall. First, he has visualization of the phenomenon. He considered crucial variables that vary with the overall shape, and he had arguments with decent reasoning. Kahn's wrong definition of boundary conditions, how he defined it was incorrect. He did not consider stern layers and electric double layers, which I quickly outlined over there. The time interval for measurement was not considered, so you have a lot of confounding variables that may affect your measurement. It did not consider depletion and accumulation. Z direction was not used, and there was no graphical data to support this analysis. Opponent's performance. The summary had some pros and cons, suggestions, and discussion. Pros are the opponent identified some minor errors such as angle of refraction and electrolysis. He also identified the lack of theoretical data. However, the opponent did not cover many huge flaws in the reporter's performance until I asked. He did not cover the electric double layer effect, and he did not identify the incorrect definition of boundary conditions, which drastically changes the shape of equipotential lines. So the first discussion topic was how would you describe z-axis curves? The opponent asked that, and the reporter said it is neither a parabola nor a hyperbola. I disagree with the reporter. It is pretty common knowledge that equipotential lines in non-metallic boundary conditions. So for example, if your liquid is surrounded by plastic, they will have the shape of hyperbolic functions. The opponent said, have you considered different conditions? The reporter said no. I think the entire purpose of experimentation and for this matter, this competition is to test different parameters and develop your own theory, etc. The opponent challenged the time interval. The reporter said the first 2 minutes. I disagree with both, as mentioned earlier. To move ions across the solution, create a stable time period that only occurs from approximately 5 to 10 minutes. Note how these depend on variables like voltage, threshold voltage, etc. The data collection should occur in this stable time period. Next discussion topic was how many points total. The equation used was for point electrode. The reporter said they used 290 points total. The reviewer thinks that the equipotential lines will still be symmetrical even if the z direction is different. Yeah. So why is there a difference between Na and Cl? The reporter said the electrolysis will be the same as water. I partially agree with the reporter. However, he missed the important point. The electrolysis will create the electric double layer effect because it will create the anions and cations that will move to the respective cathodes and anodes and create the important effect over here. So overall, I don't even get what this is about. The opponent said the overall products will be more. Hydrogen atoms are bigger. The reporter said the symmetry will not change, and he also correctly identified that hydrogen atoms are not bigger. Also, the last time I checked, oxygen was 2 minus and hydrogen was plus. Therefore, 2 oxygen was 2 plus and 1 oxygen is 2 minus. Last time I checked, water was H2O. So adding those together, they are equal. They should be symmetrical. Finally, did you consider products that will not dissolve? The reporter said sodium and potassium sometimes won't dissolve. The reviewer believes that the concentration of each element in solution will affect the shape of the lines. And, yeah, no, sorry. The reporter missed the Poisson-Boltzmann equation and the Gouy-Chapman model. They sound like really complicated terms, but actually in the field of equipotential lines, they have been around for 100 years. I don't know why you would create your own theory when there is already one existing. You might as well reinvent all of your variables. He also didn't mention redox reactions, the electric double layer effect that occurs at anodes and cathodes, the z direction equipotential lines, the time interval of measurement as mentioned earlier, and he also misunderstood the boundary condition as the difference between metallic and non-metallic points. Because metallic points have electric fields that are parallel, whereas non-metallic points are more random. Thank you.
So for concluding remarks, first I would like to thank the reporter and the opponent and the reviewer for making some suggestions. For the opponent suggested us some ways that we can conduct our experiments with more accuracy, and that the reviewer presented us with some new theory that we haven't heard before, and we should check them. We should graph them out and then disprove them before we use our theory. And then there's one thing I would like to talk about is that about the electric double layer effect, we have in fact already talked about it here. Although I don't know that the name is double layer effect, the fact that the electric field made by moving ions is already discussed here, which makes a dent in the line. So I believe that the reviewer did not really understand what I'm talking about, and then instead trying to whatever. So we also believe that the AC and DC parameter that the opponent talked about is very important because AC will make the electrolysis product, it will prevent electrolysis products from flowing to the minor electrodes. So we should try that in the future as well. Thank you.
Thank you. Is there any questions?
Okay, first, this alternating current, how do you define potential at a point? Starting maybe with the opponent. You are the first one to mention this.
The potential at each point?
No, at the probe.
Oh, at the pole, so at the
Any position.
Can you please rephrase the
If
question?
it's an alternating current,
Yes.
right? If AC is alternating current, right? Then what's the potential at a point? What do you mean? It's time varying, right?
So the way we conducted was we.
No, I just ask you, what's the potential at a point? Is a fixed value or what?
It should be alternating.
It should be what?
It should be alternating.
So what's the potential? What do you mean?
So it is varying. It might not be a constant.
You mean the amplitude? Or, because it's harmonic. It's just harmonic oscillation.
Because when we are applying alternating current, we're applying to voltage.
And the field will alternate too.
Yes. So, but the data are collected at the separate poles, so it will not be.
At every point in between. Right?
Yes.
Between the two.
Yes. Yeah. So that's why it makes it a symmetry.
Maybe because you seem to agree that AC is a good idea. I want to hear from you.
I believe that since in representation I have showed that the difference in the potential will not actually affect the shape, but only the density. So, in the case of alternating currents, while the potential at every little time interval will change, because as we know, alternating current runs on the sine wave, but however, the shape will not be affected that much, and that is what we want.
The shape of
Yeah, because whether or not the difference of the potential is 4 volts or 5 volts.
Okay. How about, maybe I will change another stuff. I think you mentioned that the electrode is in the water, right?
Yes, correct.
And if you only have maybe the electrode, it's not infinitely long. But you are using a theory of infinite long wire, which is also is thin. You make these two assumptions. The wire, which is infinite. Second, the wire, its cylinder is approximated as a thin line. I thought you mentioned you will explain, but I didn't hear you explain why that formula works in this case. You use the formula which is applicable for long, thin, current carrying, voltage, constant voltage line.
The reason that we think it applies here is that because at the point of contact with the water, a long conducting wire, and in our case, the waves as the electrodes are all perpendicular to the water surface. And
So the what is always perpendicular?
the electrodes.
Yeah, it is perpendicular.
Yeah, so the
Is it?
electricity flowing into it is just the same as the non-conducting wire and all perpendicular to the water.
You think? There's no theory for it?
No, we'll improve this in the future.
Okay. How about you?
Can you please repeat?
It is important in this experiment to verify that you use the short electrode. Actually, it doesn't have to be long, right? But the theoretical formula you are checking against is for a very long conductor, which has a radius small compared with the length, because If it's not, you should use the image chart method, because the two electrodes should be equipotential surface. And it is one approximation we make, and the other is long. It is a long wire. The formula should work for the long wire, but now you don't have that. And I'm asking you, do you know why that works? This works, but do you know why?
Wait, sorry, what works? Because what I was
Why the formula works?
for what?
In this case, for the equipotential lines or surface, actually we're talking about lines. The lines we will follow the theoretical formula more or less.
Because at a certain point you have an XYZ direction that's projected onto the XY plane. When you have an infinitely long wire like the reporter did, that changes the gradient of the Z direction, which is what I was trying to imply earlier.
I think that one important thing is that above the water is air. It's an insulator.
Yeah.
So the currents, everything remains in the same, almost the same horizontal plane.
Yes.
And that's why, I think that's why it's not, I think, I know, because it's same electromagnetism. This is, okay. So
I'd like to correct my answer on the previous question.
AC?
AC, yes.
Very good.
So yes, I believe there is definitely oscillation and harmonic change of potential, and as what he just mentioned, it's a sine wave. So that's what makes the potential alters.
I'm sorry, I used that most. I think this last, so we should allow more.
So for measuring this equipotential line in water, is the water the ionized water, or is that if you use a small bias, would you get anything?
We use tap water. So we use tap water. So so there are a little bit of deviation that I want to show here, because I believe that is caused by the trace amount of ions existing in tap water. So the same phenomenon can be seen if you look at it very close, just not that pronounced.
So there is a sort of a minimum this bias to the electrode,
yes,
for you to get some data. So what? If there's no ion at all, how do you measure the potential? Maybe.
That is considered tap water as a pure dielectric. So it's very charged.
It's like a vacuum.
Slightly.
Like a vacuum. If I put two electrodes here, how do you measure the potential?
Sorry?
I'm saying if you have two electrodes in vacuum,
Yeah.
how do you measure the potential profile?
In vacuum, it's probably
it's gonna be
impossible.
the same. Wait, will it depend on radius? It's gonna
There has to be ions.
Well, I'm giving you a challenge.
with that.
Can I answer the question? I believe that when there is no ions, there will be no current, so therefore there will be no potential. However, even if the water has no ions,
There
the
will
water
be
will be
potential.
I disagree, because just because there's no current doesn't mean there's no potential. That is an incorrect statement.
Okay, maybe you can continue this after the premise. scores. First, the scores for the reporter are 7, 8, 7, 5, 8. And then the scores for the opponent are 7, 6, 7, 6, 7.
Thank you.
And finally, the scores for the viewer are 7, 7, 7, 6, 7. Okay, then that concludes this session.